What's up, guys? Welcome back to the 12 ISLs of Christmas. Today we're going to be discussing 2024 ISL C2, a nice combo problem from only last year's shortlist. And the problem is, let n be a positive integer. The integers 1, 2, 3, all the way to n squared are to be written in the cells of an n by n board, such that each integer is written in exactly one cell, and each cell contains exactly one integer. For every integer d with d dividing n, the d division of the board is a division of the board into n over d squared non-overlapping subboards, each of size d times d, such that each cells contain an exactly one d by d subboard. We say that n is a cool number if the integers are written on the n by n board, such that for each integer d with d dividing n and 1 is less than d is less than n. In the d division of the board, the sum of the integers written in each d by d subboard is not a multiple of d. And we want to determine all even cool numbers. So we notice even here, so that definitely has to be important to us somehow. But first, let's go ahead and knock down some small cases. So let's try out n equals 2 first. Then we could just have this board here. And we get 1, 2, 3, 4, suppose. Then there's literally no divisor between 1 and 2. So this just automatically works. Now we look at n equals 4. Then we have the numbers, suppose 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then we know that for d equals 1, we don't have to include that. For d equals 4, we don't have to include that. So now we just need to look at d equals 2. Then the sum of the numbers on each d by d subboard is not a multiple of d. So the sum of the numbers on each 2 by 2 subboard must be odd. But then here we see that the sum is even. And same for all of these guys here. So how can we fix this? Well, let's go ahead and try swapping some numbers. So for example, over here, instead of having 5, 6, 7, 8, we could instead have something like 5, 7, 6, 8. And notice how we swap the 6 and 7, because then we get odd plus odd plus odd plus even, which is odd, and odd plus even plus even plus even, which is odd. So we can do something similar here, 9, 10, 11, 12. And then finally 13, 15, 14, and 16. And notice how we use this swapping idea again. And indeed, the sum of the numbers in each section is odd. So that means that n equals 4 works. Now let's take a look at n equals 6. I've already listed out the numbers in the 6 by 6 grid. So now we just need to check some values of d to work. We can look at d equals 2 and d equals 3. Those are the only ones that matter to us. Let's start with d equals 2. Then the sum of the numbers inside this subgrid here is even. And similarly, we have that some of the numbers here are even, and so are they for the rest of these grids. Let me go ahead and draw on the grid lines for these 2 by 2 grids real quick. So we have an even sum, even sum, even sum, even, 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 even. And we want all of them to be odd. So what happens if they were instead all odd? Then we have an odd number of evens, which stands out a lot because that means that their sum is even, but if we have an odd number of odds, then their sum is odd. So this gives that the sum is even. But on the other hand, if we have something like odd, 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 which we want, then that means that we have odd sum. And that's bad. So that means that n equals 6 does not work. We can attempt to generalize the approach we used for n equals 6 to other n. So let's see what happened there. In the n equals 6 case, we had 9 2x2 grids of numbers, which I'm showing here. So we had 9 of these 2x2 grids, and if all of them were to have odd sum, then that's bad. Let me go ahead and highlight these. So if all of these 2x2 subgrids have odd sum, then we want this to somehow be bad. Because if we do it like 1, 2, 3, 4, 5, 6, and then we just continue enumerating it downwards this way, then we always have 2 odd numbers inside each square. So the sum of the numbers should be even, 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 even. And that means that the sum of all the numbers in the grid is even. However, if we look at the case where all of these sums are odd, because that's what we want in a good division, then that would mean that we have an odd number of odds whenever n is equivalent to 2 mod 4. And this means that we have odd times odd, which is odd sum. And that's a contradiction, which means that n equivalent to 2 mod 4 automatically do not work. Okay, so we know that n equals 2 and n equals 4 work, and n equals 6 and n equals 10 do not work because 2 mod 4 numbers don't work. But wait, you may ask, why does n equals 2 work then? Isn't 2 equivalent to 2 modulo 4? Well, yes. But recall that when in the n equals 6 case, we divided it into 3 2x2 subgrids, or 9 2x2 subgrids. So each of these is the 2x2 subgrid. And the sum of the numbers in each 2x2 subgrid is odd, and we consider the problem statement for that d equals 2. But the problem is, when n equals 2, that means that d is not equal to 2, because d is less than n. So that means that n equals 2 is fine, because of the problem condition. So it seems like whenever we have n is an odd number times d, where that odd number is greater than 1, then that's bad. But if that odd number is 1, then it seems to be fine. So this will motivate our approach later on. Okay, so now let's see what's going on for n equals 8. So let's draw the grid. And the way we can draw the grid is as follows. And this is the easiest way to draw an 8x8 grid. We first split this in half, then we split each of these guys in half. Then we split each of these guys in half. And there we have it. We have our 8x8 grid. So let's see how we can use this to motivate our approach for n equals 8. Well, notice how in our first step, we already had these four 4x4 grids. And we already solved the problem for n equals 4. So this might mean something. Because what if we have a construction for n equals 4 here? And then n equals 4 construction, and then n equals 4 construction, and n equals 4 construction. Then that would mean that we repeat numbers, obviously, but this otherwise seems to work because it definitely satisfies d equals 2, but then d equals 4 breaks. So 1, we need to add numbers accordingly, and 2, we need to fix the d equals 4 case. So let's go ahead and call the n equals 4 construction S for now. Then S has numbers 1, 2, all the way to 16. Then we want another quadrant to include the numbers from 1 to 17, from 17 to 32. So we could do S plus 16. So that's 17 all the way to 32. Then S plus 32, then that's 33 all the way to 48, and then s plus 48, which is 49 all the way to 64. Then in d equals 2, the sum of the numbers in each grid in 2x2 grid in S is odd. And when we add an even number to each number in S, we don't change that property. So now we just need to fulfill the d equals 4 condition. And recall how we used something similar when solving the n equals 4 case. Meaning that when we had like this grid here, we noticed how we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and we solved that by swapping numbers. Can we swap numbers in this case? Well, yes, but we have to be careful. Because if we try swapping them in the normal way, like 1 and 32, then we violate the d equals 2 case, because then we make the sum of the numbers in a 2x2 board even instead of odd. So we need to swap two numbers of the same parity while turning this from a multiple of 4 to a non-multiple of 4, and similarly for this one. So how can we change how can we change whether each one is a multiple of 4 but not whether it's a multiple of 2? Well, the answer is that we just look at the numbers that are 0 mod 4 and 2 mod 4. So for example, look at this 2 here and look at this 32 here. We can swap the 2 and 32, and let's see what happens there. If we swap the 2 and 32, then this one decreases by 2 mod 4, so that becomes from multiple of 4 to not multiple of 4, and something similar happens for this one. So then we get that we can do something similar here, 34 and 64. And swapping these guys, again, makes the d equals 4 condition work. So that means that n equals 8 works. So 2, 4, 8, does it suggest something interesting? Well, it definitely suggests that the only n that seem to work are when n is a power of 2. So let me go ahead and write that down real quick. So it seems like the only n that work are n equals 2 to the k. And let's prove that these work by induction on k, because we use the n equals 4 construction to prove that n equals 8 works. So let's assume that n equals 2 to the k minus 1 works. Then we want to prove that n equals 2 to the k works. So suppose we have our 2 to the kn minus 1 grid, S, and we're going to try doing something similar as we did for n equals 8. Then we shift the numbers in S by, suppose, S plus 2 to the 2k minus 2, because that's how many numbers are here. Then we get S plus 2 to the 2k minus 1, and then S plus 3 times 2 to the 2k minus 2. And this covers all numbers in the 2 to the k times 2 to the k grid. But now we need to figure out the case where d equals 2 to the k minus 1. Because if d divides 2 to the k minus 1 and d is less than 2 to the k minus 1, then by the inductive hypothesis, it works for S and therefore it works for all of these guys, since this doesn't change whether it is a multiple of 2 of d. And now we can just figure out what happens when d equals 2 to the k minus 1. Well, the sum of the numbers in S here is just 1 plus 2 plus all the way to plus 2 to the 2k minus 2, which is, if we evaluate it, 2 to the 2k minus 3 times 2 to the 2k minus 2 plus 1. And this, unfortunately, is a multiple of 2 to the k minus 1, because 2 to the k minus 3 is greater than k minus 1, whenever k is greater than 2. And it is greater than, and when k is greater than or equal to 2, which we are assuming is the case because we're going upwards. So that means that we need to do the swapping strategy again. But at the same time, we cannot change the residues modulo 2 to the k minus 2. So what do? Well, we can take 2 to the k minus 2 from here and 2 to the 2k minus 2 from here and swap them. And that fixes the issue. And we can do something similar down here. So that means that by the induction, all powers of 2 work. Okay, so now we know that all powers of 2 work. So let's see if we can prove that all the other numbers don't work. But let's continue going. So n equals 12, we don't know if it works or not, but we're guessing that it doesn't work. Because if it did work, then we'd got like 2, 4, 8, 12, 16, and that doesn't seem to follow a clear pattern. N equals 14 doesn't work since it's 2 mod 4. N equals 16 works since it's a power of 2. So now we're just left with what happens when n equals 12. So let's go ahead and draw our grid here. Okay, so we have our 12 by 12 grid here. So what's so special about 12? Well, let's see what was special about powers of 2 that might have made this work. Notice how when we have powers of 2, we have that d is always even. So we only really had to worry about even numbers. But in the case where we have 12, we could have that d is odd. So let's see what happens when d equals 3, because that's the one odd divisor of 12 that's between 1 and 12, exclusive. And then in d equals 3, we have here, 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 and here, here, and here. And the sum of the numbers in each of these grids is not a multiple of 3. But we can't really do much with this because we can't combine things as we did earlier. Because if we try combining 3 grids, then we're just left with a bunch of stuff behind. So you know what? Let's try out d equals 4 instead. Then this becomes very interesting since we then split into an odd number of grids. So what can we do here? Well, recall what we did for n equals 6. In this case, we just used the d equals 2 case and got odd plus odd plus odd a total number of odd times. So could we do something similar for this here? Well, unfortunately we can't because the sum of the numbers in each of these grids is not odd. But we could try doing something similar, because what if it's a multiple of 4? Well, it can't be a multiple of 4. But can the sum of the numbers in this grid be odd? Well, let's see what happens. Because if we split this into the grids here, motivated by our approach for n equals 2 to the k, then we get that each of these guys is odd, 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 odd. So that means that the sum of the numbers in this grid here is even. But it's not a multiple of 4, which forces it to be 2 mod 4. And this similarly forces all of these guys to be 2 mod 4, 2 mod 4, and all the way through. And that means that the sum of the numbers in this entire grid must be 2 mod 4 times an odd number, which is 2 mod 4. However, we get 1 plus 2 plus all the way to plus 144 is equal to 144 times 145 over 2, which is divisible by 72. And 72 is not 2 mod 4. In fact, 4 divides it. So that means that n equals 12 does not work. So the obvious question is, can we generalize this strategy for the rest of the n? Yes, we can, because we can write n equals b times 2 to the a, where b is greater than 1 is odd. just like how when we used n equals 3 times 2 squared, or even for n is equal to 2 mod 4, we did n equals b times 2, where this was the odd part. So let's see what's going on here. If we have our entire grid here, then notice how we used n equals 2 to the a to solve the case when n equals 12. So let's see if we can do that again. So suppose that we have a b by b board of 2 to the a by 2 to the a subgrids. Then we have 2 to the a by 2 to the a subgrid. Then we want to show that this is 2 to the a minus 1 mod 2 to the a, in spirit of what we did earlier. And we can do this by induction on a. When a equals 1, that's just given by the d equals 2 case. When we have that 2 to the a minus 1 works, then we have that this is 2 to the a minus 2 mod 2 to the a minus 1, and then that, and that, and that. So that means that the sum must be a total of that times 4, which is 0 mod 2 to the a minus 1, but not 0 mod 2 to the a, which forces it to be 2 to the a minus 1 mod 2 to the a. So therefore, each of these guys is 2 to the a minus 1 mod 2 to the a. And similarly for all of these guys. And then since we have b squared is odd, that means that the sum of the numbers on this grid is equivalent to 2 to the a minus 1 times an odd number, which is just this mod 2 to the a. But then we have 1 plus 2 plus all the way to plus b squared times 2 to the 2a, which is just n squared, is equal to this times that plus 1. So b squared times 2 to the 2a times b squared times 2 to the 2a plus 1 all over 2. Then that means that we have a factor of 2 to the 2a minus 1. But then that means that it's 0 modulo 2 to the a, and that's bad. So why is b greater than 1 important? Well, we can't really divide it into a b by b grid if b equals 1, because that violates this condition, which is why powers of 2 are so special in this sense, and why they work in this problem. So what are the main takeaways from this problem? Well, the first one is to look at small cases, because this can definitely help. Because when we look at small cases, we get that we can get an idea for what the answer should be. And inside this case, we found that the answer should be powers of 2. And to construct powers of 2s, this brings us to our next takeaway, is to try fixing things when possible. Just like how we fix things when n equals 4 by swapping numbers, and as we did in the powers of 2 construction. And now we just needed to show that powers of 2 did not, other non-powers of 2 did not work, which brings us to our third point, is find special things about the n that work. Because by looking at special properties of powers of 2, we were able to motivate the main idea that proved that n that were not powers of 2 did not work. So those are the 3 main takeaways from this problem, and using those we were able to crack this open. So thank you so much for watching this video, and I'll see you in the next one tomorrow.